Can you see a PowerPoint presentation now?
Yeah.
Perfect. So guys, in the unit number 2, we learned derivatives and limits, right?
Yeah.
So now we're going to proceed studying many other ways of their applications. So as you may remember, I told you that, for example, if we have a function of distance, we can get a function of speed using the distance function by taking derivative of it. Can you recall it?
Yeah.
So what I'm saying is that derivative of a function over time of a distance would be a function of speed. But today you're gonna see that it's not the final space for us, not final edge, it's not a limit for us, because in fact with derivatives you can keep on taking the derivative of a function unless it turns into 0, right? Because once you get 0, every following derivative would be the same, because 0 is a constant, and we remember the constant rule that derivative of a constant equals 0. Make sense?
Yeah.
So unless we have components in this function, derivative may have sense. For example, if we have a quadratic equation like this, okay, first derivative of this one would be 2x plus 1, right? Double check it, guys.
Yeah.
So now we're gonna see that if we differentiate it again, so we apply differentiation 2 times to the initial operation, it's gonna be a derivative of this. So derivative of the derivative, and it's gonna be equal to 2.
We take the derivative of the derivative.
Sorry?
We're taking the derivative of the derivative.
Exactly. Because if you remember, derivative, in fact, is just a name of name of the component of the function, right? Because if this is our initial function, so its derivative, it would be a function that describes rate of change, right?
Yeah.
But derivative of the derivative would be the function that describes rate of change of the rate of change, right? And if we're talking about in terms of distance and speed, so the second derivative of the function of distance would be first derivative of function of speed, and it would be function of acceleration.
So we solve for the acceleration then. The derivative of the derivative is the acceleration.
Not acceleration, but function of acceleration. Because this equation would look like something times t, time. Remember? Because time is a variable. And we're gonna solve for acceleration in this case. If initial function was function of distance, when we take 2 derivatives of that function, you see, you can look at it like steps, step by step. First derivative of a function of a distance. Alan, can you tell me what is that?
Oh, sorry, can you repeat the question?
First derivative of a function of a distance.
The first derivative of the function. I don't understand the question really.
What would be the first derivative of a function that describes what distance we pass?
So the what?
What is the derivative, Alan? What is the derivative? It's a function of rate of change.
Yeah, the average rate of change.
Not the average, but instantaneous rate of change. Average rate of change was before. Now we turn into instantaneous when we can study rate of change at specific point on the graph.
Yeah.
So what is the rate of change of distance? How do we call it?
Is it's delta D, but is it
It's
velocity?
speed or velocity. So delta t of s is going to be v.
So the derivative of a function is the velocity?
Derivative of the function of the distance is the velocity. But what would be the derivative of a function of a speed, of the velocity?
Acceleration.
Exactly, because acceleration, it's a rate of change of velocity.
Okay.
Great, guys. So we got this first step. And this is some of the intuitive interpretation of the derivative, because when we talk about distance, it's something familiar to us in a three-dimensional space, right? But later you're going to see that derivatives could be applied to objects that we cannot imagine. Okay?
Hmm.
It's just an intro for you. So write down this formula. Second derivative of function of distance equals first derivative of function of velocity equals function of acceleration. Let me know once you finish. Any questions so far?
Wouldn't the A be the prime with the instead of the S? Because it's the second derivative.
Sorry.
Wouldn't the A and the S be flipped because the A is the second derivative?
In this form, it doesn't matter because we just say they are equivalent, no matter whether 1 equals 1 or 1 equals 1. Here, basically, this is right. You would say function of velocity equals second derivative of function of distance.
Yeah. Wait. No, but aren't we starting with the speed? Wait, no. What does S stand for?
S stands for distance.
Oh, can we use
or
D? Is it S or just can we use D?
No, it's in every book you're gonna see an S notation.
Okay. But isn't distance the original equation?
Pardon?
Wouldn't the S be the original equation?
If you're taking derivative of it and finding acceleration, yes, S would be original original equation. But as well, for some cases, imagine here in this direction, it's easy, right? You can imagine why derivative of distance is velocity, why derivative of velocity is acceleration, because it's intuitively understandable. But what was before function of distance?
F of X, like
It could be some random function FOT. Okay, so for example, if we have FOT, some function FOT, and we differentiate it, sorry, wrong place here in front of function sign. If we differentiate it and it turns out that we're getting function of distance, it means that FOT would be original function for in this case.
Okay, and then if we differentiate S of t, we get V of t. And if we differentiate
Sorry, slow down. If we differentiate what?
S of t, S
Yes.
prime of t, we get V prime t. And if we differentiate
No. Keep in mind that if you take S prime of t, because prime stands for differentiation, remember?
Yeah.
If you're saying prime, it means you differentiated this function by t. So S prime of t would be V of t. And V prime of t would be A of t.
Okay.
Now it makes sense?
Yeah.
Write it down like this again. Because in this case, FOT is just an imaginary function that may be maybe before function of distance. You see what I mean?
Okay.
As well, we can differentiate function of acceleration, and we're gonna get some other function.
Okay. So if you differentiate f of t, that equals the displacement.
Don't be so stick to it. It's just one of the forms. It's not something you gotta remember. It's just a way of imagining it, representing it on the paper. So sorry, go ahead with your question.
So if we differentiate f of t, that equals the displacement. If we differentiate displacement, we get the velocity. And if we
Yes,
differentiate that, we get acceleration.
brilliant, brilliant. In fact, all true.
Okay.
FOT, don't hold on to it. I just gave you image that we may have some formula
F of t
before
would be
that.
like that, right?
Pardon?
F of t would be that I circled, right? That just
In
that.
this, in case for distance,
Will be
you
bigger,
see,
probably, wouldn't it?
yeah, because if you recall the physics, acceleration, function of velocity, it's at squared divided by 2. It's function of velocity. And you see, once you differentiate function of velocity, your exponent of a variable gonna decrease, right?
Mhm.
Differentiate this for me, and you're gonna see that function of acceleration is AT. Acceleration times time, if acceleration is constant. If we
Okay,
have constant acceleration, okay?
I got it.
So in this case, I just gave you an abstract example. If you have quadratic equation, then the first derivative of it would be linear equation, and the second derivative of the quadratic equation would be just a constant. And you gotta see it, because once you differentiate, remember it, power goes down by 1. And if in your initial function you had greatest power of 2, you differentiate it 2 times, what would be the greatest power in the equation?
What do you mean by the greatest power? Oh,
And
that would
greatest power of the variable,
be 1.
0, if you
Oh,
differentiate 2
yeah, 2
times.
times, yeah, it'd be 0.
2 times minus 1. Oh, we have one new guest.
Oh, meshed.
While they're setting up their PC, let's move on. Or let's wait, maybe. Okay. Let's move on. So here, I would like you to do this because it's very important. I wouldn't tell you why it's important just now because you wouldn't understand it, but you have to know how to evaluate surface area and volume of certain objects. And this was in your geometry class, I believe, before. Guys?
Yeah.
Oh, okay. So we just plug in the numbers.
For example, in number 4, tell me the equation
Oh, I'm looking at number
for
5. Never mind.
if we're looking at number 4, tell me the equation for the um
Perimeter,
and no area of square,
length times width, or base times height.
or A times B, right? So if we know it's square, what it means that A equals B, right?
Yeah.
Because sides are equal, 90 degrees. So we know we have we have perimeter 20. If you were to write in your papers, and that's one important stuff, because I saw you guys in your test, you did few unfortunate mistakes because you're not familiar with how to express it on the paper. So in this example, you would write A, perimeter equals 20 centimeters in the brackets. So now we say that A equals perimeter divided by 4, and that equals 20 divided by 4, or equals 5 centimeters. Now we say that the surface area, S, it's also stated as S, as a distance. So S, surface, right, equals A square, or 25 in this case. Am I right?
Yeah.
So please tell, Yusuf, tell me the answer for B. How would you evaluate it?
For B,
Yes.
so
How to find surface of the rectangle?
Length times width.
yeah,
Good job, Yusuf.
Oh, sorry.
wait, so find
Determine the area of each figure.
oh, okay.
8 times 6, how much is that?
8 times 6 is 48.
Correct. Tell me, what is the quantity of the surface area?
Like the area?
Yeah, how in what units do we measure it?
Uh, centimeter squared.
Great, absolutely right. Now circle, radius 7. Again, the correct way to write down exercise like this, you start with given, you write double dots, and you state radius equals 7 centimeters, okay? Sorry.
I don't know what that was.
So, tell me the surface area of a circle, guys.
Surface area for the circle.
It's PR a square.
Okay. So then you just plug in pi times 7 squared.
Divided by 2.
Oh, divided.
Or let's double check it. Surface of a circle.
I know the
A PR a square. Just PR a square. Not
pi
divided by 2.
pi r squared.
Pi r squared, yes.
Okay. 153 point. Do you want the entire
Wait,
one? Or do you want me to
sorry,
round?
123. What is that?
153.
What is that?
The area.
Read the question. Leave your answer in terms of pi where applicable.
Oh, okay. Pi 49.
Great. Pi 49. D, circle.
The circumference. Okay, that's 2 pi r.
Great.
Um,
So we say that length of a circle equals 2 pi r, or equals,
circumference is 2 pi r.
oh, sorry.
Oh, sorry, I was looking at.
Wait, sir.
So we have the circumference. We want to find the area.
Yep.
Okay, so oh, so then if we take we rearrange that formula for circumference, so 2 pi r. We have c, we have pi, and we have, if we rearrange it to solve for r, and then plug it back into the formula we used for the last question.
Great set of actions. So in this case, radius would be square root of, or not, or 6.
How do you solve that so quickly?
Because I know that 12 pi equals 2 pi r. I divide it by 2, I get 6 pi. It means 6 equals r.
Good. Can you write it down so I could write it down in my book?
So 12 pi, we know that the formula equals 2 pi r, and it's equals, I'm pretty sure that the sign for you, what sign did you use for circumference in school?
C.
Okay, let's be C. So based on this, I write arrow like this. That's how I like to write it down. Based on this, you know, like outcome of this is that r equals 12 pi divided by 2 pi, or equals 6. 12 pi divided by 2 pi, do you understand why?
12 pi divided by, yeah, because circumference is 2 pi r.
Yeah, and we just simply divide left-hand side and right-hand side of the equation by the common factor.
Wait, sorry. So 2 pi r equals circumference. You
Yes, equals 12 pi.
you divided the 2 pi from the right side, brought it to the left side, so it's c over 2 pi, and then you plugged it in, equals r. Yeah, okay. Well, I'm writing down number c. Sorry, letter c.
Letter C, so circle radius.
Wait, so what's the formula for area of a
So formula for area of a circle would be pi r squared.
okay.
I remember it was something pi r square divided by 2. It's like on the tip of my tongue, like it's supposed to be there. Maybe it's somewhere else. No, this is correct. So, did you wrote it down?
Hold on.
Yeah, I got it down.
So now you know those formulas, right? Write down all of those formulas. Please write the area of a square, area of a rectangle, area of a circle, area of a, oh no, or just circumference. Write it down as well, okay? Because if you have it in your copybook, you can refer to it quick. You don't need to Google it every time, you know.
Yeah.
How I prefer to do it in my school age, I was dedicating first page of and the last page of my copybook for formulas, and I was writing down all the formulas on those 2 pages, and then when I was struggling to remember them, I was just opening one page or the last one. You got an idea, right?
Yeah.
In math, it's even more important to write down everything in your pen and the pencil, because that's how you actually remember it. You wouldn't remember it just by reading it. Your basically everything, your arms, your eyes, your breath should remember these formulas. You understand what I mean?
Mhm.
It should be like intuitively for you.
Mhm.
Let me know once you finish writing it down.
Yeah.
Awesome.
So, unfortunately, because I'm late, we don't have time to review test together. I'm going to post. Would you like it me to email it directly to you, the results?
Yeah. Email
Okay.
me.
So, but don't be worried. You did all right. There are a few mistakes for both of us, and generally, I'm satisfied how you did the test. Great job, guys.
Thanks.
Are you finished?
Yeah.
Yeah.
Perfect. Let's not waste time. I want you to do this example on your own, okay? Because here it's pretty much the same, but we have different variables, different input. For example, in this task, you're given with the volume. You're also given with the formula for volume. So pay attention. It's just for your practice to write something on left-hand side, write something on right-hand side, and be able to extract information that you need from this equation, okay?
Mhm.
Like we
Um,
did in the example D, remember?
Yeah.
We just did it. This is pretty much the same, but overcomplicated to practice. I believe in you guys. I believe you can do it. So let's not waste time on it.
Can you send me the presentation? Because it's a
Yes.
little bit small and hard to see.
Sorry, I will adjust it like this. Is it
Okay.
better now?
Yeah, a little bit better.
A little bit. Let's
Thank
make
you.
it much better. And this is much better.
Yeah, it's good now.
So, we're done with this. Here is the beginning of section 3.1. High order derivatives. This what are we gonna focus on?
We're not gonna do number 5.
Pardon?
Are we not gonna do number 5?
Not now, because it's time consuming.
I'm just
Uh,
copying.
you can copy the question and please do it on your own. It's for your own sake, okay? Because this is pre-acquired skill. If you struggle with this, you're gonna struggle in future.
I don't know. This seems pretty easy to me.
But you see, we already spent around 15 minutes on these two tasks. And it's unfortunately it's not acceptable.
Okay. Yeah, I got it.
Brilliant. I'm gonna post this presentation to Google Drive so you can download it from there. And this is examples from the reading material that we have.
Mhm.
So let me read this for you. And I want you to read the book on your own as well, because trust me, from my school experience, if you read what they actually give you, it basically simplifies your life. So derivatives arise in the study of motion. Remember, at first we wanted to know how fast is something moving at a specific point. Then we discovered limits. Then we generalized rules for limits and applied them with composite functions, right? With the higher order functions. So the velocity of a car is the rate of change of displacement at a specific point in time. As you said, Alan, it's velocity is derivative of displacement.
Mhm.
We have already developed the rules of differentiation and learned how to interpret the derivative at a point on a curve. We can now extend the applications of differentiation to higher order derivatives. This will allow us to discuss the applications of the first and second derivatives to rates of change as an object moves in a straight line, either vertically or horizontally, such as a space shuttle taking off into space or a car moving along a straight section of a road. You get it?
Yeah.
So why we're looking for linear displacement? Because, for example, in tasks where you're talking about distance, you're not talking about path that the object traveled, right? You're only talking about distance from the starting point. How far, for example, somebody getting away from where he started. Make sense?
Yeah.
In
Yeah.
another task where we have rockets flying, for example, we usually have equation of their height in the flight. Remember?
Yeah.
That's what we had. Rocket height during the flight can be described as a formula, etc., etc. And height is also linear displacement because it's only along z-axis, as well as, for example, displacement of a car. We treat it as a linear displacement. For example, if you look on the surface of a planet as two-dimensional, right? X and Y. So car would move along one of those axes because car can move forward and back, left and right. And that displacement we can measure. So high order derivatives. The function y equals f of x has a first derivative y equals f prime of x. The second derivative of y equals f of x is the derivative of y equals f prime of x. So what they say here, it's pretty messy, but they say that the second derivative of y would be derivative of f of x, f prime of x. So what they say, basically, you take derivative of this, and you take derivative of this. Here, it's very weird why they mentioned y both here and here, because we know that it shouldn't be the same. But you got the idea, right?
Yeah.
Yeah.
We discovered at the beginning. Here is a simple example with exponential function. So let's say we have 10 times x to the fourth power. First derivative would be 40 times x to the third power. And second derivative of 10 times x to the fourth power, 10 times x to the fourth power, and we're looking for second derivative. Oh, here in this example, first derivative would be 40. How to solve it? You would find the first derivative first.
And
So
then,
you cannot skip one stage here, right? You gotta find first derivative, then differentiate the first derivative. And second derivative of 10 times x to the fourth power would be 120 times x to the second power.
so 120x to the second power, that's the acceleration in the example.
Yes, but 10 times x to the fourth power is not function of displacement. It's just random equation.
So then 40 is the displacement, the 41, that's the displacement.
No. None of this is related to speed, acceleration, or displacement.
Like as an example, if we did
Yeah, if you do it the same, so 10 times x to the fourth power would be function of distance if it's the first one, then derivative of this would be velocity, what we see here,
Yeah.
and then second derivative of this would be acceleration, as
Okay.
well as the second derivative of 10 times x to the fourth power is 120 times x squared.
Yeah.
But keeping this has nothing to do with speed. Yeah, it's
Okay.
just an example.
Okay.
Perfect. So for complex functions, here we have difference rule, right? An
Yeah.
exponential rule. So if we're finding first derivative, we're applying both of those rules here. And if we are looking for second derivative, we're again applying both of those rules here, because you see first derivative still consists of two components, of two terms. So you have to apply same rules. It doesn't mean that the rules are always going to be the same as for the first derivative, because after differentiation, equation can change its appearance, right?
Yeah.
Because, for example, now you can see that second derivative of this is 12 times x subtract 10. And in this case, you would apply multiple constant rule, 12 times x, and constant rule, because 10 is just a constant. It has no variable in it.
Mhm.
While in the previous step, when we found the first derivative, we were applying exponential and difference rule.
Yep.
Perfect. This one, note it for yourself. This is how you represent the second derivative in Leibniz notation. So if first derivative we express it, it's d over dx, right?
Mhm.
And let's say dy over dx, it was already differentiated function, right? If we have dy over dx, it means we differentiate something.
Yeah.
And if we apply differentiation again to this, result would be d s square y divided by dx s square. And it's not a coincidence that d square is here after d and square here after x. It's going to be like that all the time. Let me know once you wrote it down.
Okay.
Yusuf?
1 second.
Yep.
Almost done. Okay, I got it.
Brilliant. Let's move on to the next slide. Here is an example how to find the derivative of coefficient, applying coefficient rule. Or, for example, in this case, as Yusuf and Alan, you did this in your test, when you saw something like this, when x divided by some other function, you simply brought it up with negative power, right?
I don't remember.
So if you have x squared divided by x, it's basically x squared times x minus 1. Make sense? Guys?
I'm just copying it down, sorry.
Yeah, so this is, in this case, we have equation x over 1 plus x. And we need to find second derivative when x equals 1. So what we do here, first of all, we transform it so it's easier for us to solve it. How is it easier for us to solve it? If we represent it as a product of two functions, and then we apply product rule and power rule.
Mhm.
Make sense?
Yeah.
So x times 1 plus x to the power minus 1, you can see it here. Then you differentiate it as normal. Remind me product rule for differentiation, guys.
Sorry, give me a second. What was the question?
Product rule of differentiation.
The product rule?
I'm gonna ask you about those rules every time because you just need to know them by heart.
Okay.
Get it out.
If f of x times g of x, remember two different functions, derivative of the product would be derivative of
Derivative
f
f of
times
x,
gx plus
f
f
of
of x. Yeah,
g prime x.
Great. In this case, so let's take a look. F prime of x. If f was f of x equals x, right? Look here. F of x equals x, right? First derivative would be 1 because x to the power 0 equals 1. Got it?
Yeah.
Perfect. X plus 1 to the power minus 1, look here, doesn't change because it's simply g of x. And g of x is 1 plus x to the power minus 1. And in your copybooks, I also would like you to write it down like this: f of x, g of x, first list of all of the elements in a row, for example, and then it's going to be easier for you to find their derivatives. Because you see the formula, okay, OF prime of x. So I look at f of x, and it's super easy for me to find derivative of something more simple, right? So
Yeah.
once you did it, you're gonna get this like equation. You see it? I highlighted it. Like this, red. You see it? After you perform all of these operations, eventually you're gonna get this. Now, what we want to do with it is to simplify it, bring it into one fraction, right? Of course, you are not supposed to, but the more components you have, the more you have to differentiate, remember? For example, if we won't simplify it first, and you would differentiate it, you would have to find, you would convert this into product and power rule, convert this one as well as we just did, then consider difference rule, okay? It's not so convenient.
Wait, sorry. I'm just trying to figure out, how did you get the, how does that 1 and then the x plus 1 negative 1?
So 1 is a derivative of f of x, because the formula of derivative of a product is f prime of x, right? Look here, f prime of x times g of x plus f of
Yeah.
x times g prime of x.
How did we get
So
1?
because f of x, what is the f of x in this case? I noted it here. F of x is x.
How?
How?
Yeah.
Why f of x is x?
Oh, because so so f of x is x and then g of x is 1 plus x to the negative 1.
Absolutely.
Okay.
You understood why?
Yeah.
Yeah.
Perfect. So now we proceed to simplify it. It's not so hard in this case. You just multiply this fraction by x plus 1 to get a square in the denominator. Is it clear?
Yeah.
Then you can join them in one fraction if denominator is the same. So once you join them together, you're going to see that you have x plus 1 minus x, or in another word, 1 divided by 1 plus x squared. Or in another word, 1 plus x to the power minus 2. Understandable?
Yeah.
So let's remember, why are we doing this? What are we doing now? Right now, we just found first derivative. You see it?
Yeah.
First derivative of initial equation. Now we would like to find second derivative. And we repeat the same power rule, their differentiation.
Why is there a x plus 1 negative 2 times 1 at the
Here, x plus 1 minus x, because in
no,
previous
right
step,
here, right here, right here. Sorry.
yeah, x plus 1 minus 2.
Yeah.
So x plus 1 minus 2, because here, this component is going to be derivative of g of x, right?
That's the derivative of g of x.
Yes, because remember, it's derivative of a composite function. So in fact, this is derivative of g of x.
Oh,
Because it's not simple function, because we have something in the brackets which is raised to the power. Remember, f o g of x, right? Composite function.
can you just run through how to solve for the g of x? The derivative.
So let's write it down. We say that g of x, we said we have f of x and g of x, right? But now we see that g of x is in fact is a composite function. So we write g of x as
1 plus x to the
no.
negative.
I would say first of all I would state that it's a composite function. Let's find some other symbol of g. Let's say h. Okay, h of some other function e of x. Okay, doesn't matter, because we would like to state that g of x is a composite function first of all. Make sense?
Yeah.
I just want to know how
How to solve it?
is this g of x right here, right?
Yes.
So how do you turn that into this? I just want to
So
know.
let's remember derivative of a composite function rule. Derivative of a composite function. So how it works? First, you differentiate what is outside, and then you differentiate what is inside. So what is outside function in this case? It's an exponential function, -1, or x to the power -1.
Mhm.
Here we simply apply power rule. So we substitute -1 for -2 because it's -1, and -1 is going to turn into coefficient, right?
Mhm.
So we're gonna have -1 times, and for that is inside function is not changing just yet. So inside function stays the same. Outside function has changed, right? You see it?
Power rule.
Use the power rule, and now we have to multiply this by the derivative of the inner function, and the inner function in this case is x plus 1. Now we multiply it by the derivative of inner function, and what is the derivative of x plus 1?
1.
Great. And now compare this to this.
So you use the power rule. You brought this -1 out the front here on the bracket,
Yes,
and then you added 1 to this,
subtracted 1
or subtracted 1, sorry.
because it's power rule.
You got -2.
Yes,
And then why did you get the 1 on the end?
because it's a rule of differentiating the composite functions, because f prime of g of x, let me write it down for you, it's equals n times f of x to the power n minus 1 times g of x, but prime of g of x. You see it?
Yeah.
Again, this test wasn't just to give you mark, guys, because we're gonna use all of these formulas in the future a lot.
Okay.
Write down this formula for yourself.
What is the n?
N is the
Oh,
power.
yeah, number, yeah. So power, so
So how I remember this product of a composite function, you differentiate what is outside, then you multiply it by what is inside, also differentiated. Here it's going to be FO G of X. Make sense, guys?
Yeah.
Alan, any questions?
Yeah. No, that makes sense.
Perfect. Also, I posted another class. You have all the formulas in there, okay? Just print it out for yourself, post it on the wall. I don't know, do whatever you can, but remember them.
I have them beside me. I just don't know which rule is it?
Derivative of a composite function.
What do you mean composite?
Complex. Compound.
Oh, okay. I have 6 of them. I have the constant function rule, the power rule, constant multiple rule, sum rule, difference rule, and product rule.
But you're missing some of the rules.
Okay.
There is also a derivative of a composite function rule and derivative of the coefficient rule
Okay.
when we divide f of x by g of x. Because it's not always the case that we can represent g of x as something to the negative power.
Okay.
Any questions about this exercise?
No.
No.
So here, again, we're applying for second derivative, we're applying derivative of a composite function rule. You see it? -2 is the power that we bring outside as a coefficient. It turns into -3 times derivative of what is inside. And inside we have 1 plus x. Understand?
Yeah.
Yeah, I'm just
Ye-
copying them.
Perfect. Let me know once you finish copying it.
And then the final answer is the second derivative, right?
Yes, in this case, we've been looking for this value of the second derivative at point when x equals 1. So
Okay.
final step would be find the equation for second derivative and then substitute x equals 1 in there.
Oh, okay, so the x plus the 1 plus x to the power of -2 is the first differentiation.
Yes,
Oh, okay.
absolutely. Follow the step. Here to here, and from this to this. Oh no, to this. Step by step. It is also important. When I was studying this at university, it's so easy to get lost in all of these calculations because you have -1 here times n here, then we need to substitute it, bring down, bring up. You understand what I mean?
Mhm.
It's easy to get lost in here. So it would be really useful for yourself at first place to know all of these formulas by heart for differentiation. It's the things that we covered in Unit 2. You can review the lecture, save the formulas. Any questions?
What was it? What was that formula? Like the that equation for that the rule? You were
Product, composite
Yeah,
function rule.
yeah.
So f o g of x,
F-
derivative of this would be equal to if just give me a second. Yep, it's gonna be equal n times f o g of x to the power n minus 1 times g of x. Or in other words, at times g of x. So this is the case when outer function is exponential. You see it? When it's exponential. Again, this is only when it's exponential. If it's not exponential, general representation would be derivative of f o g of x times derivative of g of x. And please review the formulas.
What's that rule called again? Oh, the chain rule.
No. Or is it? Is it the
I-
chain rule?
I searched it up because I didn't know what the rule was called, and it says chain rule.
Yeah. True. It's chain rule, sorry. Yeah, this is the correct formula for general case. When you don't know what type of external function do you have, okay?
So you use chain rule whenever there's a fraction and a power outside of it.
You're using a chain rule whenever you have function inside another function.
Like
Because
that?
in this case, yeah, like that. Because in this
Okay.
case, we have linear function, 1 plus x, inside the exponential function, x
Okay.
to the power minus 2.
Yeah.
Brilliant. Any questions?
No.
So here, let's talk about velocity and acceleration. Motion on a straight line. One reason for introducing the derivative is the need to calculate rates of change, as we discovered before. Consider the motion of an object along a straight line. Examples are a car moving along a straight section of a road, a ball dropping from the top of a building, and a rocket in the early stages of flight. You know, three regular imaginative tasks, yeah, that you can get, imaginative problems, because that's what you usually do. You drop a ball in your physics class or wherever. When studying motion along a line, we assume that the object is moving along a number line, which gives us an origin of reference as well as positive and negative directions. Did you get it?
Yeah.
Yeah.
You're gonna look into it again. So what we say, it's really important to understand that we have positive and negative direction. So positive would be away from the starting point, and negative would be towards the starting point.
Yeah. I learned that in physics class.
Great. The position of the object on the line relative to the origin is a function of time and is commonly denoted by S of t. The rate of change of SOT with respect to time is the object's velocity, as we discovered, and the rate of change of the velocity of this with respect to time is its acceleration. The absolute value of the velocity is called speed. Any questions so far?
No.
Perfect. So let's move to this next slide. Here, notation in Leibniz format, what I showed you, you see exactly the same. Isn't it?
Yeah, we have this burned down.
You have it already. The units of velocity are displacement divided by time. And that's important to remember because what is the velocity? Numbers of meters that you cover over some period of time, right? So it's really important to remember units, like we know units for area, for linear distance. You get it? Because knowing the units can give you a hint on how it works. Because, for example, if we know that the acceleration that if we know that acceleration is the meters per second squared, it means that we should have t squared somewhere, right? Because seconds are squared here.
Yeah.
And we should have meters. We should have distance in this formula. Since we are assuming that the motion is along the number line, it follows that when the object is moving to the right at time t, v of t greater than 0, and when the object is moving to the left at time t, v of t less than 0. If v of t equals 0, the object is stationary at time, right? When the speed equals 0, it means the object is not moving. So here, when the object is moving to the right time t, means speed is positive.
Yeah.
Because we are getting farther from starting point. If we're moving to the left, it means speed is negative. We're moving to the left along the line. The object is accelerating when a of t and v of t are both positive or both negative. For example, if your speed is positive and your acceleration is negative, it means that acceleration, let's say, imagine if this was line that describes the direction and let's say scale of velocity, okay? And imagine if we have second line that looks backward and it describes acceleration. What it makes you to think? It makes you to think that acceleration acts on the to the inverse direction of the velocity. Thus, for example, if something accelerating me negatively, it means I'm decreasing my speed, right?
Yeah.
At the same time, if my velocity would be negative and acceleration negative, it would mean that I'm moving backwards and I'm accelerating backwards.
Okay.
So, so in total, I'm not decreasing my speed, but I'm accelerating it.
Yeah. So if your acceleration is negative and your velocity is negative, it means you're decreasing your acceleration in the
Negative direction,
negative direction.
basically, yes. Or you're increasing your acceleration. No, you're, I would say you decrease it in positive direction and you increase it in negative direction because minus plus minus.
Yeah. So if your v is plus and your a is negative, it means you're decreasing acceleration in the positive direction.
Yes.
Yeah. Okay.
Yusuf, you got it?
Yeah, I think I got it.
Brilliant. So clear the drawing and what is the time? Let's review last example, okay? And you're free to go, guys.
Okay.
So example 2, reasoning about the motion of an object along the straight line. An object is moving along a straight line, its position described as function of distance or displacement to the right of a fixed point is given by the graph shown. So we see that over time we moved farther away because you see here's the distance at the toppest point, and then we turned backwards because distance began to decrease, right? So on this part of a graph, from here to here, from 0 to 0.2, time equals 2. Do you see it,
Yeah.
guys? So in this range, we were actually going with positive speed,
Yeah.
and we have to define whether acceleration was positive. But I can say you for sure that acceleration in this case was negative because
Hmm?
because at some point we turned around, right? We turned backwards.
Which
So
graph?
huh?
What graph is this? Is this like a velocity graph?
This is graph of displacement, distance,
Okay. Okay.
S of t.
Yeah.
To see why acceleration negative or velocity is positive, you have to plot graph of their derivatives.
Okay.
So analyzing this graph, I can say right away that the range from 0 to 2 seconds, let's say, my object was moving in the positive direction because distance from the starting point was increasing. And after that, until the moment of time 6, my object was actually moving backwards. And here you gotta check if acceleration was positive, because, you know, once you reach 0, you should still be accelerating for a little bit to keep moving backwards, right?
Mm-hmm.
Because let's say my speed was 50 kilometers per hour, right? At point 2, t equals 2, my velocity equals 0, makes sense?
Mm-hmm.
And after that, my velocity should be negative because I'm moving backwards.
Yeah.
So, and if I would like to keep moving backwards, I should get some more acceleration, because if my negative acceleration stops at top point, I would not go anywhere. My acceleration gone. You see it? But if we, in this graph, we see that we're actually moving backwards. But at some point, we stop again and move forward. You see?
Yeah.
So my conclusion that somewhere in between first stop and second stop, for some time I'm accelerating, and for some time I'm decelerating to stop. Makes sense? It's just like riding a bicycle. You start pedaling, you increase your speed, then you push your brakes and you start to slow down. Pushing brakes is an example of negative acceleration.
How can you assume that though?
Because I just explained you my reasoning, because first of all, I'm looking at that how distance changes.
Yeah.
Here, I spotted that distance changes positively. So
Yeah.
it means my velocity is negative or positive.
Yeah.
But I also mentioned that at some point of time, my velocity equals 0. So it means I
You're
should,
at rest.
I definitely should, must have negative acceleration somewhere there in order to make my velocity equals 0.
Okay. Yeah.
But you can find those answers without visual analysis. All you have to do is just find the derivative, and if your derivative is positive or negative, it's gonna give you understanding of the direction.
So like whenever you mark the line down the middle, that's not the
Not the exact moment of time
Yeah.
when
You stop.
acceleration changes from positive to negative or from negative to positive. It's just my prediction that somewhere in
Yeah.
this range,
From here.
acceleration should definitely change from positive to negative, from
Okay.
negative to positive.
It could be at 1, it could be at 5.
Yeah.
Yeah, it could be at any moment of time. And to find that when it happens, we should apply derivatives.
Okay.
Because, for example, if we take a look at the derivative, we definitely gonna see whether velocity at this point is positive or it's negative.
Okay.
Perfect. So I just explained you intuitive way of analyzing the graph. Right away, I almost finished solving this question only by looking at the graph. And now let's read what they want to know, okay? When is the object moving to the right? When is it moving to the left? And when is it at rest?
You already solved that.
We already did it,
Yeah.
Yeah.
you see? And it wasn't so hard. Not at all. Here, they're gonna show you solutions, show you reasoning. This is how it's supposed to look in your book, but nobody cares how it looks in your head. If you
Yeah.
can solve it in your head first, it's much easier to represent it on a paper.
Yeah.
Let's take a look at what they say here. The object is moving to the right whenever distance is increasing.
Yeah.
In other words, velocity positive. From the graph s of t, it's increasing from 0 to 2 seconds, as we found it. And for time greater than 6. And we see there, here, in fact, when time equals 6, you see our graph like deflects from x-axis and goes up again.
So it's at rest.
So it was at rest here at 0.6. And after that, he began to grow again, you see? So
Yeah.
distance increasing again. But in this example, we don't know how it acts after this
Yeah.
line. It may go up and down. It may go like this all the time. By the way,
Doesn't really matter
is this going to be differentiable, guys?
yes.
No, look, why? It's so sharp. We have sharp corners here and there. Furthermore, for one x, we have several y values. You see it?
Okay.
This is sorry, maybe I confused you. I was asking about my my random red line, if it was
Whenever I
differentiated.
thought you drew it, I thought you were drawing. I thought like you made a mistake with the drawing, and you're supposed to make it like how it looked in the picture.
No. It's just my
Yeah.
my way of testing you if you remember derivatives, guys. So all we don't need to add anything extra to this graph. It's already giving to us as it is. So let's analyze what is given. So from the graph, object is moving to the right when time less than 2 or greater than 0, or for the time when it's greater than 6. Is it clear?
Yeah.
For a period of time from 2 to 6 seconds, the value of displacement is decreasing. So velocity is going to be negative.
Yeah.
So the more object is moving to the left. At time equals 2, the direction of motion of the object changes from the right to left. So velocity at this point equals 0. Same one for point of time 6.
Yeah.
Clear?
Yeah.
Brilliant, guys. I really love how we work. So this is a diagram that is going to represent motion of such an object. So you see, we moved the long line to the positive direction. At point of time t equals 2, we turn around, moved back, and moment 6, we turned around and went forward again.
Yeah.
Brilliant, guys. That's it for today. Do you have any questions?
No.
No.
So I kindly asking you, please review the formulas of the differentiation all the way up to chain rule,